for the next 2 classes. So this will be a 2-class lecture and activity. Don't forget, Project 4 is due on Wednesday. I've seen a lot of people either very close to completing them or already done, so that's great. Don't forget, Friday, your quiz is on classes 28. Now remember, class 28 was the polynomial regression section. We switched the order in our schedule. And then classes 29 and 30. I sent out an email to everybody over the weekend. Some of you may be checking your GCC email, some of you may not. But what I said is for class 38 homework, class 30 homework, do not pay attention to the instructions that are in the homework. In other words, do not pay attention when they say use the rational number theorem to find your zeros. Or if they say use Descartes' sign rules of sign, what is it? Descartes' sign rule, I guess. I never teach it, so Descartes' sign rule. What I said is to ignore these 2 things and just use the methods that we learned in class. Methods used in class. So if you're looking at a big monster polynomial and you're trying to figure out what your first 0 is to do long division, throw it into your calculator and find a 0. And then you start your long division. Then whatever's left, if it's not quadratic and you can't tell or you can't factor it, you throw that into your calculator and get another 0. So you get to your quadratic when you can use your quadratic formula. So I don't want you worrying about thinking you've got to learn something that we didn't cover in class from reading. Now, sometimes, I'll say you've got to make sure you read the section because I can't cover everything in class, but this is one time where you don't have to pay attention to this. If you want to, just for your own knowledge, that's fine, but you're not going to be responsible for either of these 2 things. Okay. So let's start off today with rational functions and their graphs. And you want to start us off, Ben?
Rational function is the ratio of 2 polynomials. That is, rational function is a function expressed e of x by x. Being q are polynomial functions, q of x is not.
So why do you think, Ben, I said q of x cannot equal 0?
Yes, 0 is not there.
Right, you can't divide by 0, right. So again, when you see the word rational function, I just want to underline the first part of that word rational, and you see the word ratio, which tells you you're going to be looking at the division of 2 things, ratio. And in this case, individually, the numerator is a polynomial. The numerator is a polynomial. What degree polynomial is the numerator? What degree is it? The numerator. Second, right. So it's a 2nd degree polynomial in the numerator. What's the leading term in the numerator? What's the leading term? Nope, that's the leading coefficient. What's the leading term? X squared, right. The leading term in the numerator is x squared. The leading coefficient is, Beth? 1. Okay. All right. So look at the denominator. What's the difference between the numerator and the denominator? What's the difference? Yeah, the denominator is in factored form, completely factored form, whereas your numerator is in standard polynomial form. Notice it's a bunch of terms, pluses on top. Sometimes you might have subtractions. So this is in standard polynomial form. Your denominator is in completely factored form. Okay. What degree is the denominator, and how do you know? What degree is the denominator? The polynomial in the denominator. And how do you know? And how do you know, Shane? You see 3x is that if you were to multiply, you'd get x to the 3rd, right? Okay, x to the 3rd. And what would be the leading term of the denominator, of the polynomial in the denominator? X cubed, right? Okay, so your project asks you about leading term. Leading term is the whole thing, not just the coefficient, the whole thing. So the leading term here is x squared, and the leading term here, if you multiply this all out, in fact, how would you multiply this out, Austin? How would you go about multiplying that out? Don't want to answer? Or you can say pass if you want.
I'll try.
Okay.
I'm a little out of this morning.
Okay.
X squared and then x.
Okay, so you would multiply these two first,
Yeah.
and you'd get.
X squared minus squared.
Okay, so then we've done with that multiplication, and then we would have that product times x plus 2, right? And then we would just go x squared times x is x cubed, x squared times 2 is 2x, negative 4x squared, and plus 2x squared. Did I screw up anywhere? 2x squared, thank you. All right. So let me see, x squared times x is x cubed, x squared times 2 is 2x squared, negative 4x times x is negative 4x squared, and negative 4x times 2 is what? Didn't do that one right. Huh? Negative what? 8x. All right. So I can simplify these two because they're like terms, x cubed minus 2x squared minus 8x. So that would be what that factored form looks like in polynomial, standard polynomial form when it's multiplied out. Notice you have 3 linear factors. So if you have 3 linear factors, you have 3 zeros and you have degree 3, right? We've learned that in the last class. All right. So the thing about rational functions is we have to take a look. I'm going to rewrite this. I'm going to ask you for help because I'm going to go to a new page. So that function we were looking at on your paper was what? X squared plus 5x plus 8 in the numerator. Is that right? And in the bottom it was x times x minus 4, x plus 2. Thank you. Okay, so the thing we have to sort of worry about is we have some trouble spots here. Okay, we have potentially some trouble spots. And remember when we were first learning about domain way back in September, we learned that the trouble spots was what made the values of x that made our denominator 0, or if we had an even root we were looking at, what made the radicand, the piece under the radical sign, the even radical sign, negative. So those were our concerns. So what would be the domain? Remember, the domain is a set. So you can either write the domain in set builder notation, or you can write it in interval notation. So what's going to be the domain here in either one of these notations? So someone want to take on the domain for this particular function in one of these notations? What you think the domain of this is? Nobody wants to take it on? Tiffany? The straight line? Okay, such that. Okay. And that's what it looks like in set builder notation. So our trouble spots here, if we were graphing this, our trouble spots would occur at what? X equals 0, x equals 4, and x equals negative 2. We're going to have some very funky erratic behavior. It's going to misbehave as erratic behavior at these spots. Okay, that kind of graph we're going to save for Wednesday's class. That's Wednesday. We're going to look at really trouble spots that could happen in 3 spots. Today we're only going to look at trouble spots just in 1 spot. We're going to take it easy and build up our kung fu techniques so that we can really take these on. Okay, so that's set builder notation. What are we going to do? How would we write that same domain in interval notation? Someone want to help me with that? Interval notation. Nobody can do interval notation for the domain? Mary, you want to try it? Mm-hmm. Union. Yeah. Mm-hmm. Right. So this is the one situation where if I ask you to write the domain and you have three trouble spots, it's a heck of a lot easier using your set builder notation than your interval notation, right? So remember, you're just looking along your x-axis and you're saying x can go from negative infinity until my first trouble spot, -2, then negative, I'm fine until I hit 0, and then I have to not include 0, and then I'm fine again until I hit 4, and then I'm okay all the way out to positive infinity. So you can see set builder notation is a much more efficient form of writing the domain here. Okay, so let's look at the first rational function. We've already talked about this domain. The first rational function is something you should be familiar with from your transformation project, 1 over x. Does anybody know what we had called 1 over x? We gave a name to this function. Reciprocal function, right. So the function 1 over x is called the reciprocal function because all it does is take the reciprocal of whatever x is. So if x is the number 2, f of 2 is 1/2. And the relationship between the number 2 and 1/2 is their reciprocals. If f is 1/10, what's the function evaluated at 1/10? What would be my answer? 10. In other words, if you put it in the long way, it would look like this, 1 over 1/10. And we all know that when we divide, we multiply by the reciprocal of the denominator. So we get 10. Okay, so that's how the reciprocal function works. And if it's negative, like -100, then our reciprocal carries exactly the same sign. Reciprocals always have the same sign. Okay, so just a little review of the reciprocal function. So where's our trouble spot with the reciprocal function? Where's the trouble spot here? When x is 0, right? This function is not defined when x is 0. So when we write the domain, this one wouldn't be a bad one to write in interval notation, but when you write the domain, you could say x, so here's the domain of our function. Domain of our function f is x such that x doesn't equal 0. Okay? In set builder notation. In interval notation, it looks like this. All the real numbers except for 0. So the question asks, what value of x is excluded from the domain, and the value of x that's excluded from the domain is x is 0. X cannot be 0. I guess if we're answering this, what value of x is excluded, you'd say x is 0, but it's really probably good to recognize that x cannot be 0. This is what's excluded. Okay, fill in the values of the table to see what happens to the y values or the values of your function as your x values move towards 0. Okay, we know we can't be 0. So what happens to our function as we move towards 0? So let's see. So if I were graphing this, here's 0, and I know I can't be 0. So I'm going to put a dotted line straight down through my y-axis like that because I know I can't be 0. And what is the equation for the y-axis? What's the linear equation for the y-axis? What does the equation look like for the y-axis? Y equals x. Y equals x? Y equals x looks like this. Never mind. Okay, I'll never mind. Okay. What's the equation for the y-axis look like? It's a vertical line. So think about the equations for vertical lines. Mary? X equals 0, right. Notice every single point, Shane, right? If you were to plot any point along that line, all the x values would be 0, right? I never memorize this, literally. I just visualize it and think about the points along the line, and all my x values would be 0. So x equals 0 is another way to write the y-axis. That's the equation for the y-axis. All right. So I know I can't have any x equal to 0, which means I have no y-intercept. So this tells me I have no y-intercept, which means I'll never cross that y-axis. Never cross it, never touch it. Never cross, never touch, okay? So I'm interested in saying, what happens to my function as I get really, really close to 0? As my x values get really close to 0, as I'm coming in from the right-hand side, and as I'm coming into 0 from the left-hand side. That's what we're going to explore, is the behavior of the function as x gets really close to 0 from both sides. So let's take a look at a table. So in this first table, notice what's happening to my x values. I'm starting with 1, and then I'm moving in closer to 0. I'm at a half, and then my x value is a tenth, and then 100th, and then 1,000. So even if I were trying to graph those points, the width of my pen would be so thick, I wouldn't even be able to get in as close as 1,000. So we're just going to look at this sort of in a theoretical sense. So in this table, the x values are approaching, whoops, excuse me, go up one table. In this table, the x values are approaching 0 from the right. That's the language we use. That's new language for you. We are approaching 0 from the right. 0 is our trouble spot, okay? So if x is 1, what's f of 1 going to be here if I'm doing my reciprocal function? 1. F of 1 is 1 because 1 over 1 is 1, okay? What about f equals a half? Now notice this is in decimal form, and we don't usually think about reciprocals in decimal form, so it's probably really much easier to think about 1/2 as the fraction 1/2. So what's the reciprocal of 1/2? 2. Because if we did it the long way, it would look like this: 1 divided by 1/2, which is 1 times 2 over 1, which is 2. So I'm going to start graphing these points on my graph here. I don't know if you have a graph. Do you have a graph on yours? Okay. So at 1, I'm 1. So I put a point right there. At 1, I'm 1. Let me make that a different color. And at a half, I move half my distance to the origin, or to 0 there, and I'm already up to 2. All right. So there I go. I'm getting really close to that y-axis. All right. Now I'm going to move in even closer. Instead of half the distance to the y-axis, I'm going to only be a tenth away. So what would f of 1/10 look like? Well, let me put it in as a fraction, because taking the reciprocals of fractions are much easier. So what's f of 1/10 going to be? 10, right. So I get in really close to 0, and I'm all the way up here at 10. Okay. So my behavior so far, my x values are moving to 0, and my y values are getting big. Okay, well, how big are they going to get? Let's see. What's f of 100th going to be? If I take the reciprocal of 100th. 100. Oh my God. So I can't even put that on my graph. It's going to be up here on the ceiling somewhere. And then f of 1,000th is going to be 1,000. So this graph blows up, it increases without bound. I'm talking faster than I can write. Let's see, without bound, as x gets close to 0 from the right-hand side, and that's how we write it, folks. This is new notation. As x gets close to 0, and that little superscript plus says I'm coming from the right. So as x approaches 0 from the right, the value of your function approaches positive infinity. increases without bound. Now, as you know, mathematicians do not like writing all these words out. So the symbols that they use is they say, the shorthand for this is, as x approaches as x approaches 0 from the right-hand side, this says from the right, the value of your function increases without bound or approaches infinity. Okay, so that's the behavior that is right here. It's going up towards infinity. So what I'd like you to do at your seats now is I'd like you to fill in this table for these values, which is approaching x from the left-hand side. So notice we're at -1, -1/2, -1/10. Fill in this and then actually graph it. Just graph what you think happens between -1 and getting close to 0 from the left. What's happening to the values of x, the values of f of x as we approach 0 from the left? So let's fill in each of these spots in our table. So when x is -1, what's f of -1? F of -1/2 is -2. F of -1/10, -10, -100, -1000. So as x approaches 0 from the left, what happens to the values of f of x? What does f of x approach? -infinity, right. And this is how we write that phrase above. As x approaches 0 from the left, f of x approaches -infinity. So notice I'm only between the values -1 and 0 here, not including 0. So at -1, I was -1. At -1/2, oops, whoa, baby. At -1/2, I was -2, and then I shot down to -infinity. So notice I never actually touch across that y-axis. I know it looks like it because the width of my pen there kind of interferes with the y-axis, but I never touch it because x can never be 0. I'll never have a point on this graph that says 0 some number. X is 0 is excluded. So the final thing I need to look at, well, before we do that, is this vertical line is what we call the vertical asymptote. Okay, it's a kind of funky word, asymptote. Okay, x equals 0 is the vertical asymptote. Okay, now a rational function can have one vertical asymptote, could have no vertical asymptotes. Or let's see, can it have no vertical asymptotes? What do you think about that? Does it always have to have at least one vertical asymptote? What do you think about that? If you're looking at a division problem, would it always have a value of x that would make the denominator 0? Yeah. So how do we finish this off? Well, you know from your transformation project what this looks like, but let's see how we talk about the rest of this. So we've talked about it getting close to this trouble spot 0. Now we want to talk about the end behavior. Okay, what happens to this function as x approaches infinity, as x gets really, really big, and as x approaches -infinity, it gets really small. Okay, so let's see. That's the next part of this. All right, so let's see. I forgot about the x and y intercept. So what does an x-intercept look like? It's some value of x that makes y 0, and our y-intercept is x equals 0, and you have some value for y. Well, we know we've already talked about the fact that we can't have any y-intercept because x cannot equal 0. So what about the, did I say that right? What did I just say? X is 0. Did I say y-intercept? No y-intercept. I only slept like 1.5 hours last night. No y-intercept. Okay. Just wanted to make sure I said it right. Okay, so we've got x0. So can we find what is x0? That's our x-intercept, right, when y is 0. So if we set f of x equal to 0 and we ask if there's a value for x that would make that 0, what would you say? There isn't any. Because when you're trying to find, when you have a rational function, which has a numerator and a denominator, and you know your fraction equals 0, the only way your fraction can equal 0 is when your numerator is set equal to 0. And since your numerator is a constant, there's no way one's ever going to equal 0. Now, if I had x squared plus x up there, then you could set that equal to 0 and find the values for your 0, right? Your x-intercept is the 0 of your function. So there's no x-intercept either, okay? So if I come back here to my graph, I know that it's not going to cross the x-axis and it's not going to cross the y-axis. Okay, so what's it going to do? Okay, so the end behavior, how do we look at the end behavior? Well, we want to see what happens to our function as x gets really, really big. So if x is the number 10, my function is 1/10. Okay, so I know what's happening here. I know that as I get close to 0, I'm shooting up to infinity. If I'm out here at 10, I'm barely above the x-axis. My y value is really, really getting tiny. Okay? What if my x value is 100th? What is my f of x value or my y value? 1/100th, which is even closer, 0.01. What happens if I go way out here and I'm at 100,000? What's the value of my function? 0.000001. So what's my end behavior look like? What's happening to the value of my function as x gets really, really big? As x approaches infinity, what does the value of my function approach? What value? 0. Okay, so now let's look at the other side. We know we were at -1, -1, -0.5, -2, and as we approach 0 from the left, we were going close to that y-axis. Now let's see what happens as x gets really small. So let's do a table for that. X, f of x. If x is -10, we're at -1/10. So we're right there again, getting really, really close. If we're at -100, we're at -0.01. It's the same exact behavior. -100,000, -0.000001. So as x approaches negative infinity, f of x still approaches 0. So we're getting really close to that x-axis, but we're not crossing it in this case because we don't have an x-intercept, right? We already discovered we have no x-intercept. It was impossible to have an x-intercept. So we say, earlier we said that this vertical, the y-axis was our vertical asymptote, and that was x equals 0 was our vertical asymptote. Now we've got a new asymptote. That's the horizontal axis. We know that as x gets really, really large, our value of our function is approaching 0, but it's never going to be 0. So think of these asymptotes. Just think about having the name asymptote. You're going to be a really lonely creature. And so when these asymptotes really like people to hug them. So notice as your function approaches either asymptote, as the values of x approach this vertical asymptote, it's like almost hugging it, really getting close. Same thing with your horizontal asymptotes. They're really lonely creatures, so you want to get your graph really close to them. Okay, so your horizontal asymptote has the equation y equals 0. That's your horizontal asymptote. So that is all of the discussion of the reciprocal function. Now you've drawn these before with your project, but you didn't have all of this notation and language. You didn't have horizontal asymptote, vertical asymptote, etc. Any questions on this? Any questions? Okay, so let's review symmetry again, because symmetry is something that kind of bugs you guys. And let's just review symmetry with our basic functions that we talk about symmetry with. If we have y-axis symmetry, the function you should think about is your parent function x squared. Because we know that if we put in x and we put in its opposite, we come to exactly the same y value. For example, if I put in 2 and I put in -2, I get exactly the same y value. So how we write that in notation is we say that my function evaluated at x and its opposite is totally the same. If I evaluate my function at x and I evaluate my function at its opposite, I get the same y value. That tells me I have y-axis symmetry. Symmetry about the origin symmetry, the function you always want to try to remember in your brain is the cubic, which flattens out at 0, but crosses right through. We know that from our multiplicity. So this is y equals x cubed, or f of x equals x cubed. We put it in function notation. And what do we remember about this? Well, let's see if we pick a number for x, like 2. Our y value is f of 2, which is 8. Now, what happens when I pick its opposite, -2? Where do I go? -2 cubed to -8, right? So notice f of -2 doesn't equal f of 2, right? -8 doesn't equal 8. What is it? -2 is the opposite of f of 2. So the way we write when we have symmetry about the origin is if f of -x equals the opposite of f of x. If that's true, then we have origin symmetry. So let's check the symmetry of the function 1 over x. So where you start is you notice both of these cases, what do they have in common? They start with f of -x. And what you want to determine, does it equal the original function or is it the opposite of the original function? So here's my original function, f of x. I want to look at f of -x. So I put in -x for x, and I look at that and I say, that certainly does not equal f of x. Doesn't equal 1 over x. But does f of -x equal the opposite of 1 over x? Yes. These are opposites, so this has origin symmetry, because the y values are opposite. Okay, so that's the type of symmetry. This is how you confirm it algebraically. You don't just pick a point, one point, to try to show it. You have to show it for all x's. Okay, so that's 1 over x in all of its glory. So let's look at one that's related to 1 over x and see what happens to that. 1 over x squared. Okay, so what value is excluded from the domain here? 0. So 0 is excluded from the domain, just like it was with 1 over x. So now let's see what happens to this function as we get close to that trouble spot. So we've got to look at what happens as x approaches 0 from the right, and what happens as x approaches the trouble spot from the left. So now we're asking, what does our function do? What happens to the value of our overall function as x gets really close to 0 from the right? So let's do a little table, just like we did before. So we're going to start with 1, and 1 over 1 squared is 1. Now we put in a half, and we get 1 over 1/2 squared, which is 1 over 1/4, which is 4. We put in a tenth, and we get 1 over 1/10 squared is 1 over 100th, which is 100. So as you can see, as we're getting really close to 0 from the right, what's happening to our y values? What are they approaching? Infinity. They're increasing without bound. They're rising. The graph is rising. Graph is rising very quickly, much quicker actually than 1 over x. Now we have to look at what's happening as we approach 0 from the other side, from the left. So we're going to look at -1, -1/2, -1/10. But now we're squaring x. So what's 1 over -1 squared going to give me? 1. So my negative sign gets removed. 1 over -1/2 squared is 1 over 1/4, which is 4, and 100. So in this case, as I approach x from the left and the right, I'm increasing without bound in both situations. So if I go down to my graph, I know that as I get close in here, I'm increasing without bound. So it looks the same on the left-hand side and the right-hand side of 0. The end behavior is exactly the same. In fact, it gets closer to the x-axis much quicker because you're squaring your denominator. So this goes like this for the end behavior, okay? And that's what f of x equals 1 over x squared looks like. Again, we have absolutely no x or y intercepts, none. Our horizontal, the equation for our horizontal asymptote is our x-axis. And the equation for our x-axis is y is 0. The arrow notation for our end behavior says this: as x approaches infinity, our graph approaches 0. As x approaches negative infinity, the values of our graph approaches 0. So a lot of new sort of symbolism. We've talked about this symbolism for end behavior before, but most of you were just saying things like graph rises, graph falls, and you weren't necessarily using your notation. But with rational functions, you have to use the notation. Okay. Just looking at this graph, what kind of symmetry does this have? Y-axis. You can see if you fold that graph right along your y-axis. In fact, I'm going to make my y-axis be dotted, okay, because I can't touch that. And in this particular case, my x-axis is the horizontal asymptote. How do you show it algebraically? You put an f of -x. So I go into my original function and put -x in, and I square it. And when I square -1x squared, I get x squared. So f of -x is exactly the same as f of x. That tells me and shows me algebraic that I have y-axis symmetry. Okay. Now, if you're using your calculators at any point to look at rational functions, yeah, let's give yourself a little space to the back of a page. What if I asked you what this function looks like? Would you have to go through a lot of like picking out x's and finding the y values if I gave you 1 over x plus 2? Why not, Adam? Right. Remember that 3 days we spent on transformations? The reason we put so much time in transformations is so that we wouldn't have to plot all these x values and then all the corresponding outputs, okay, the y values. We learned that if we know what the parent function looks like, we know what this parent function looks like. Now, I know there's a way I can insert a graph here. Where is it? Is this it? No, that's a table. Where is the graph? I can't remember because I always put them in. Maybe I don't have it up here. Do you see graph? Nope. Okay, so I'll go over here to my gallery, type in x, y axis, what it gives me. Nope, nothing there. My content, gallery essentials, mathematics. We'll get there somehow. Wonder which one it is. Algebra, no. I think it's paper backgrounds. Let's see. There we go. Okay. So we know that 1 over x looks like this. Well, I should go through 1, 1 if I'm going to be exact. All right. So we know what the parent function looks like, and all of its behavior is centered literally around this vertical axis. So not exactly centered, but the trouble spot is that x equals 0. What does this tell me? What kind of shift am I doing here? Am I outside the function and I'm going to do a vertical shift, or am I inside my function and I'm going to do a horizontal shift? What does this look like? I'm inside, because if f of x is 1 over x and I do this, f of x plus 2, I'm changing my input. That now looks like this. So how am I shifting? I'm shifting horizontally, and in what direction? To the left. Horizontally to the left 2 units. So do I have to think about all of that stuff again? No, all I have to do is say it's going to look just like the parent function, but I'm going to pick that parent function up and move it 2 spots to the left. That's all I'm going to do. So transformations allows me to put my vertical asymptote in right there, which is x equals -2. Now, do I have any intercepts? Well, let's see. When x is 0, what's y? 1 over 0 plus 2 is 1/2. So I have a y-intercept here. It's right there. That's the only difference. I don't have an x-intercept because my numerator is constant. So except for that one little change where I have a y-intercept, I can draw this graph really fast. Really fast. Just like that. I'm just sketching it. Okay? So literally, it looks exactly the same except for it's been shifted to the left. So you don't have to plot all these points. That's the great thing about knowing transformations of your parent function. So that's the idea I want you to employ. You have 3 problems in about 25 minutes. And so I want you to stay focused. You're going to be doing some type of transformation of either 1 over x or 1 over x squared. You're going to be filling in all this information. So let's look at this first function. 1 over x minus 5. What's my parent function here? What's the parent function? The reciprocal function, right? So I'm looking at f of x minus 5. I'm working on my inside. There's going to be a horizontal shift here. So that should get you going, okay? When you're done, I have the answer key up here, so you can check your answers. The other thing I started to tell you and forgot is that when you want to graph, what's the one we just did, 1 over x plus 2? When you want to graph one of these rational functions, make sure you put your denominator in parentheses, and make sure your mode is on dot, not connected, because it's going to make it look like it goes right through your vertical asymptote. So you go to your mode button right here, and you come down here, and usually it's on connected because it connects all your points, but you want it to fill in each solution individually. And then when you graph it, you'll see there it is, okay? So you notice that the graph is approaching x equals -2 and dropping down, falling, and as x approaches -2 from the right, it's increasing. So that's the one change you want to make in your calculator. Okay, have fun. Use your flags if you need me for any question at all.